So, we have been discussing testing of digital circuits. Okay. Okay. And we had talked about the single stuck-at fault model. So, as we mentioned earlier, there can be defects in our circuits which are manufacturing defects. So, for example, two wires can get short circuited, uh, or a wire can be open, a transistor which is supposed to be a switch may be permanently closed or permanently open. There can also be dust particles, right? So, if a dust particle settles down between two metal lines, it will definitely short circuit the metal lines. So, there could be many such manufacturing defects, and our intention is to model these defects using a fault model. Okay. So, in the single stuck-at fault model, we said that any wire, okay, in this example there are three wires A, B and C. It can be either stuck at 1 or stuck at 0. Okay. So, this is a stuck at 0 fault at A, this is a stuck at 1 fault at A, and similarly B0 can have stuck at 0 or stuck at 1, and C can have stuck at 0 or stuck at 1. Okay. And we have assumed that only one of these faults exists in the circuit. So, we do not allow multiple stuck at faults, right. We do not assume that there can be a situation where A is stuck at 0 and B is stuck at 1 at the same time, right. The idea is that if you test for single stuck at faults, they tend to cover a number of multiple stuck at faults as well. So, and the multiple stuck at faults, you will also agree that in a large VLSI circuit, the fact that simultaneously a wire here is stuck at 0 and a wire here is stuck at 1, etc., the chances of that happening are somewhat low. So, we do not consider multiple stuck at fault models. There are other fault models like the bridge fault model. Okay. So, in a bridge fault, what can happen is unintentional short circuits may occur. So, let us take this circuit here. So, this is A, B, C, D, E, F and G. So, an unintentional short circuit may happen between E and F, okay, or it could happen between E and G, or it could happen between B and C, right. So, two wires can get short circuited. Okay. It can be a what is the reason for such a short circuiting? Once again, as I mentioned to you, these metal lines may be running very close to one another, and as a result the etching process may not remove enough metal between E and F, and as a result E and F may get short circuited. So, that could be one reason why there could be a bridge fault. Okay. So, this is also a common fault model that is used, right. So, let us so there are two kinds of bridging that are allowed. One is called as AND bridge and the other is OR bridge. Okay. So, suppose I take this circuit, if let us say E and F have a bridge fault, in the AND bridge model, it appears that there is a fictitious AND gate between E and F. Okay. So, there is an AND gate, that this is a fictitious gate, and this guy will feed both the E and F. So, this is the way the circuit behaves now. Okay. So, the original circuit was supposed to do A B plus C plus D. So, this is what was the original circuit supposed to do, but the new circuit will do A B dot C plus D. Okay. So, this point here will produce A B dot C plus D, and of course, this OR gate will continue to produce the same thing. Okay. Because if you call this x, and the same value of x is coming here, so x plus x is x, right. So, A dot B dot C plus D. So, this is the fault. Okay. The logic has changed because of bridge. We could also have an OR bridge. So, in which case, as you can guess, there is a fictitious OR gate that gets induced. Okay. So, this is a fictitious OR gate. Okay. This is an OR bridge. Okay. So, what will be the new logic? The new logic will be A dot B plus C plus D. Okay. And in this example, the bridge fault really did not did not really result in a different logic. Okay. So, the faulty circuit and the good circuit unfortunately behave the same way. In this particular example, the OR bridge cannot be really detected, okay, because there is no difference between the good circuit and the faulty circuit. Okay. All right.